CFU in chapter 3.2 where we got in depth with the correlation coefficient R and how it can be used to help us with describing the strength of and the direction of our linear association. So let's take a look at the first problem here. It says, does social rejection hurt? We often describe our emotional reaction to social rejection as pain. Does social rejection cause activity in all areas of the brain? Or does social rejection cause activity in areas of the brain that are known to be activated by physical pain? If it does, do we really experience social and physical pain in similar ways? Psychologists first included and then deliberately excluded individuals from a social activity while they measured changes in brain activity. After each activity, the subjects filled out questionnaires that assessed how excluded they felt. The table below shows data for 13 subjects. Social distress is measured by each subject's questionnaire score after exclusion relative to the score after inclusion. Okay? So the values greater than 1 show the degree of distress caused by exclusion. Brain activity is the change in activity in a region of the brain that is activated by physical pain. So positive values are actually showing more pain. Okay? So we take a look at our data here. Okay? We have social distress for each subject and brain activity. So we're going to take a second and enter these into list 1 and list 2 because it says discuss what the data shows, follow our 4-step process. So we're going to state, plan, do, and conclude. So take a minute, pause the video and just enter the social distress values into list 1 and the brain activity into list 2 because in the plan we are going to do a scatter plot. Alright, so hopefully you have your data in list 1 and list 2. Now we're going to kind of run through our 4-step process here. So again, the problem asks you to state what we're trying to find here. So when we talk about the state, what are we trying to actually answer? So the question becomes, does social rejection cause activity in areas of the brain that are known to be activated by physical pain. That's the question that we're trying to answer. Okay? So what's going to be our plan? Okay? Well, the first thing that we're going to do is we're going to make a scatter plot. If the association looks linear, we will compute the correlation coefficient. All right, so I'm going to actually do that. So up here, I take a look, I'm going to actually use this space right here to do my scatter plot. So when I'm looking at my scatter plot, what makes this one a little bit more interesting, it's going to be kind of different for some of you, is I'm going to move the x-axis technically up, okay? Because my brain activity, or let me just start it this way. Here is social distress. So when I look at those values, they're basically going from 1 to just under 4. So I can just go right here and go, start at 0, go 1, 2, 3, 4. But if I look at the brain activity, which this is going to be brain activity, those values are going from basically I'd say about 0.15 to negative 0.5. So I might start here and go negative 0.5 and have my 0 be here, and then 0.05, 0.01, and 0.15. Sorry, 10 that should be. So negative 0.05, 0, 0.05, 0.10, and 0.15. You can do it above and below the axis and still see it, but I like to kind of get that axis sometimes out of the way. Okay? So now I need to start graphing these points. So 1.26 was negative 0.055, so just going to put a point. And then 1.85 was 0.04, so a little bit down below. So I'm just taking my time and trying to graph these points. 1.1 was negative 0.26, so that's up here a little bit more. Whoops, that's a little bit off, sorry. I'll move it because I went inside one instead of outside. So again, these don't have to be perfect, but you should still be fairly accurate. 2.5 was negative 0.17, same level. Then 2.67 was 0.17, and then 2.01 is about 0.02. 2.18 goes to 0.025. 2.58, 0.207, 2.75, 0.033. So I'm getting a lot of points kind of clustered here. 2.75, finally 0.64, so up here a little bit more. 3.33, 0.077. Now I need to draw my point, and 3.65. So I'm going to have to look at the calibration. So there, I have my scatter plot. So I'm actually doing the do right now, right here. This is the do. I'm making my scatter plot. So now as I continue with my do, I want to note what's going on. So I'm just going to note my scatter plot shows a fairly strong linear association. Whoops, a fairly strong linear, I forgot, positive, fairly strong, positive, linear association between, in this case, our social distress and brain activity. I want to calculate out R. So an R equals, so I want to get that correlation coefficient because I'm going to have a conclusion here that I'm going to more than likely use this to help support my answer. So how do we calculate out R? So I have my calculator here, and you can see the data's in list 1 and list 2. So how do we do correlation coefficient? So we go to our stat menu, we go to calc, and you can either choose number 4 or number 8. Since number 4 is right there, we want to do the linear regression. Go ahead and hit enter, and your R value should pop up. Now, if your R value doesn't pop up and you are in class, you did not, turn your you did not turn your diagnostics on. So there's a couple ways you can turn your diagnostics on. So those of you who might be gone watching this, hit your mode key. Depending on your age of your calculator, what you can do is then go to the very end and you'll have this stat diagnostics here. You want to make sure that's on. Now if your calculator is really old, then what you have to do is you have to go second 0 and you have to scroll down, and this is what takes a little bit longer, is you got to scroll down to where it will say diagnostics on. So you can get it one or two ways. So this takes a little longer for me. So I can go diagnostics on, enter, and then repeat your steps. Stat, calculate, number 4, and your R should be on. So my R is 0.8782, which really tells me I have at least since the pattern looks linear, this reinforces it since that's fairly close to 1. So now I just want to write a conclusion in the context of the problem. So what are we actually seeing? We're seeing that, when we are excluded, okay, does appear to, trigger that pain response. The higher the social distress that you had, that is definitely associated with an increased amount of activity of pain sensing areas in your brain. So let's put that in words here. So I'll have my conclusion. Okay. So social exclusion I'm having trouble spelling today. Does appear to trigger a pain response. Okay. And then we want to talk about how is it triggering it, or what's the relationship. So the higher, since it's going in a positive direction, social distress measurement those are associated with an increased activity in the pain sensing areas of the brain. All right, let's turn to the second problem. So in number 2 here it says all brawn. The figure below, so this is actually going to correspond to the diagram down here below, okay, right here, says the average brain weight in grams versus the average body weight in kilograms for 96 species of mammals are located down there. There are many small animals whose points are in the lower left overlap. So you can see a lot of the points congregate here in the very bottom. Okay. It says the correlation between body weight and brain weight is 0.86. Explain what this value means. Okay. So for the most part, all the points except for a few are falling within the line. So we could definitely say that we have a strong positive linear association between the body weight and the brain weight of mammals. So let's put that as a sentence real quick. It means there is a strong positive linear association between the body weight and brain weight of mammals. So now in B it says, what effect would removing the elephant have on the correlation? Justify your answer. So in today's lesson we took away these points that could drastically change the correlation. Elephant is definitely right here one of those influential points. It's close to the line and it's causing the correlation to be probably much stronger than it actually is. Okay? So what would happen if I remove this point? Well, it's going to decrease the correlation. So I'm going to start by saying that. Removing the point or the elephant point would decrease the correlation or the correlation coefficient. Now we have to justify our answer. Okay? Why is this happening? Okay? Well, since this point is far away from all the other points, but yet close to the overall pattern of the line, okay, it is an influential point. Causing the correlation to be closer to 1. When removing it, it should go down. The R value should go down. Wow. All right. Last one here. Love this problem because it shows you how correlation is really good for linear measurements. So it says strong association but no correlation. The gas mileage of automobiles first increases, then decreases as speed increases. Suppose that this relationship is very regular, but as shown in the following data on speed, miles per hour, and mileage per gallon. Make a scatter plot of mileage versus speed. Right? So let's do that right now. Okay? So I'm going to move this up here for a second, and I'm going to sketch this graph real quick. So here's speed, okay, and this is mileage. Okay. So if I look at my values, my speed is really, I'm just going to count by tens real quick here. So 10, 20, 30, 40, 50, 60. And my mileage starts at 24, so I might, just count by fives here. 5, 10, 15, 20, 25, 30. I go past 30, doesn't look like it. All right, so at 20, I'm at 24. At 30, I'm at 28. And then at 40, I was at 30. And then at 50, I came right back down. Okay. So there's my scatter plot. Okay. Now it says the correlation between speed and mileage is 0. It says there'd be no linear association at all. Now it says explain why the correlation is 0 even though there's a strong relationship between speed and mileage. Well, remember that correlation is a measurement of linear association. If I look at this, I have really a beautiful parabolic pattern. And so if I'm trying to find a line of best fit, more than likely my line's either going to go this way or it's going to go this way. And notice how the points are counteracting each other. Okay? So this particular plot has a great strong nonlinear relationship, hence why the linear would give you something close to 0. So I'm just going to kind of note here, correlation, again, if we remember, is a measure of the strength of a linear relationship. Between 2 points or 2 variables. Okay. A nonlinear relationship and actually, you know what, this one might be a better looking. No, I still like the parabolic. So a nonlinear relationship, so I go back to here, whoops, didn't want to change colors here. A nonlinear relationship, like in this case, a parabola, okay, would produce, or I should, a nonlinear relationship would produce an R value closer to 0. All right, so that ends 3.2.